Howdy guys. So I've got some new stuff to showcase regarding the latest features of my game engine. So first of all, let's start educ32 and see how it behaves at certain cases of sprite rendering in my test map. Let's rock. So this is 8-bit classic render mode, which is, as you might know, suffers from these artifacts because it's unable to resolve depth conflicts on pixel level, instead of just sorting the sprites according to their distance from the camera, resulting in sprites popping out of behind each other, like here and here. Well, this is annoying, of course. It works. It's working the same way regardless of whether the sprites are opaque or transparent, but it's only the oldest and old school mode of rendering. Here's another mode. It's polymorph that just uses Z buffering. Classic mode didn't use Z buffering, but here it is. It uses Z buffering to resolve depth conflicts between the sprites which happen to intersect, or just in a nutshell, it just can't handle transparent surfaces properly, so it just renders these cross of transparent polygons. Well, these are 3 sprites, so they are just look pretty much the same as they do in the classic render. But there's also polymer render. Maybe it will handle this case better. Let's see. Well, everything is pretty much the same. We see some dynamic lights appear near the switches, but these transparent surfaces, well, they certainly look a bit better, but you can see that they're still wrong, because some portions of sprites simply disappear behind other sprites. You can see these white sprite behind the red one, and black one is hiding behind the white surface. So it's totally lame, and it's pretty much every modern game is looking close to either polymorph or polymer render, and very few existing engines actually can perform any depth peeling or other complicated techniques to improve the look of intersecting translucent polygons, objects, and other stuff happening during the game. And this is quite ubiquitous. It's not rare at all. Most volume fog effects and other stuff, it requires such cases to be handled correctly. And here it is. Let's try it, the very same map in Brahma render. Okay, Now it looks like it used some sort of Z-buffering, because, well, the intersecting surfaces look well, this is suggesting, clearly suggests that Z-buffering is used, but there is no Z-buffering actually. You can see that the transparent surfaces are correct. Here the level of transparency of each surface is, you can see all 6 permutations, easily all the 6 permutations of these 3 sprites at each sector of this image. So you may ask, how the fuck did he do that? Isn't it some sort of depth billing or other, and done in pure software in 8-bit color mode? You can see that the transparency is handled by a lookup palette, leading to some color distortion. But let's see. First of all, I'm switching back to single thread mode, and disable anti-aliasing, and disable the true perspective, so it just does now, it does shearing, vertical screen shearing, like it does in old classic build. So this is just for the render to do a single pass, so you can trace how it's actually done. And here it is. First it renders the surroundings, static geometry, and now that's the way it rendering the sprites. It's global const-z scan line level subdivision of the scene, and it can handle virtually any complicated structure in incorporating various types of transparency, because each sprite, all of them are displayed simultaneously, alternating between all of them at the level of scan lines. So this technique is far more robust and versatile than everything that was being used in game engines. Well, it's deemed to replace the Z-buffer, and yeah, it actually leaves the Z-buffer unnecessary, because every sprite, every object in the scene is correctly placed and occluded by preceding sprites in front of it, and you can see that these switches don't pop out from behind each other anymore, and these corners are completely rendered with proper proportion of each sprite. It's not order independent transparency, it's just their order of transparency is always correct because of the nature of the rendering pipeline. So let's see another test map I've been doing for some years. Well, it's actually not that old, but let's type this name, it's called mertests. Source mertests. Okay, start Brahma, and here the interesting part is well, every part is interesting in some sense. There are non-Euclidean portals, there are transparent water, and there is the room which explains why Z-buffering actually sucks, because it is way too limited for structures like that need some sort of order-dependent transparency. Well, the multiple translucent polygons overlapping is quite common, and here you can see that it's totally correct. It's a bit slow, but it works, and the only artifacts you can see, they are caused by sprites disappearing because their parent sector falls out of view by the thread context it's rendered inside. So there are also Fresnel reflections. This is darkened window. It's dark gray glass, which has some red portions, which use legacy Duke 3D palette effects, so they're a bit weird, but working just to show that any portal can be colored and can be exposed down or up, because their renders is actually high dynamic range. Even in 8-bit 256 color, it remains high dynamic range, in which can be exposed freely with a vast range of values of light, the amount of light, even the reflection, which has some neat fall-off from 100% to some few percents from head-on. This is the nature. This type of reflection naturally occurs on all boundaries between media having different index of refraction, and you can see that the dynamic range is preserved, and although this surface I'm clipping it to white, but actually it is not white, it is just a very bright shade, so it remains this way even if darkened by some sort of reflection or a light filter. So the light filters are also high dynamic range aware, making this engine, well, there's also prioritized rasterization of polygons when they placed and on top of each other, but actually they are coplanar, so they are strictly on the same plane, and there are subtle Z-fighting artifacts which can be spotted, but actually the engine copes with them pretty well, and when using Z-buffering it would look a lot worse, and game designers have to move the polygons apart, a bit apart from each other, so the Z-buffer could resolve their depth depth conflicts more efficiently. And here prioritized rendering makes the sprites go in preferred order. First it renders brown square, and the greenish gray square goes, and the arrow is placed on top of both, and you can see that other nice complicated structures are possible with global const-z simultaneous rasterization technique. There is also some sort of complicated geometry, just to show that it's some sort of stress test for the engine that takes its floor capacity to the extreme. It still suffers from some hollow mirrors, which can be spotted right here occasionally, but it gives reasonable frame rates and can be optimized even further later. This location is also a sector over sector effect. Well, standard sprites, voxels, I'm redoing it, so these are meant to demonstrate that voxels can be also mirrored. If we load, we should just call duke extra to make the voxels working. Okay, return back to the engine, and well, the mirrored versions are not rendered correctly within the version of my voxel rendering, but it does a good job at displaying proper cubes, and after some optimizations and refinements, will replace the previous version of voxel rendering row time, making them more higher quality. So it's also portal which connects remote locations, and you can go underwater. It is surface meant to perform total internal reflection, but this has been disabled so far for a reason, but later it will look like this if I change the texture of this wall. You can see that this is actually a block of water, solid block of water that does total internal reflection. Looks this way, so that water surface begins, and seen from inside, it's 100% reflection, like in real physical optical environments. Well, it's not perfect so far, it's not always correct, but it works, and proof of concept prototype is pretty much working as it should. Well, so here it is. See you next time. Thanks for watching, and all the other stuff. I'll do something another later. Okay.